For some unknown reason, the first minute or so of the audio didn't get on to the video recording. However, the gist of what was said went something like this. Good evening. I'm David James, and I'd like to welcome you to this Institution of Engineering and Technology Sussex Network talk. It's my great pleasure to introduce Jeremy Hopkins, our speaker for this evening. Having studied electrical and electronic engineering, Jeremy spent a number of years in electronic circuit design and software design. However, in 1987 he moved to Sussex to join a flight simulation company and worked in that industry until retiring in 2020. So I think with 23 years experience, Jeremy is well qualified to give us a talk on flight simulation. Jeremy started by giving us a brief overview of his career up until he retired.
Thompson decided to call themselves Thales. We all moved up to, in 1994 when they acquired Hughes Rediffusion. We all moved up to Crawley and the plant in London was closed. Renamed as Thales. And then in 2012, when I joined Singlelink Miles, I was working on military aircraft simulators, so for Tornadoes, Harriers, Hawks, that sort of thing. In 2012, Thales sold their commercial aircraft simulation to L3 Link UK, so we became part of Link again. And by that time, I had moved from working on military aircraft to commercial aircraft. So I transferred to L3 with that, and Thales Training and Simulation up at Crawley now does military aircraft simulators only. And L3 then in 2017 merged with this Harris to become Harris Commercial Training Systems, and that's up at Crawley, and that's where I was working until I retired in 2020. So, flight simulation, commercial aircraft. I'm sure you've all seen some sort of simulator. Some of you might remember back in the day on the Krypton Factor, people would fly a simulator. That was one of our Hawk simulators that we produced at one time. And then this one here, this is the Air France 787 simulator. While I was working on commercial simulators, the company made primarily Airbus and Boeing simulators, because that's the main aircraft that you'll find on a commercial flight. There's one or two odd ones that they did from time to time, but basically it was Airbus and Boeing. Although they did both, I worked mainly on the Boeing simulators and only very little on the Airbus. So this was the Air France 787. For about the last 8 years of my career, I was working primarily on the Boeing 787 Dreamliner, and I was working on this one in Paris for about 4 weeks over in Paris back in 2018. Level D, the simulators have different classifications of what level of training they provide, but a full flight simulator like this is what's called level D classification. What that means is that the pilots have what's called zero flight time training. They'll go through their normal classroom training, small aircraft flights and things like that, but they'll do their final training on the aircraft type in a simulator like this. First time they fly a 787, for example, they will be sitting in the right-hand seat as a first officer with a qualified captain with them, bunch of passengers down the back. That's the first time they will fly the real commercial aircraft, because it's a zero flight time training. The reason that they can do that is there's a very rigid certification of these before they go into training. I'll mention that later. I'm not going to go into much technical detail of these, but I'll go through the main components that make up the simulator. So obviously there's a flight deck. The pilot has to sit in a flight deck. Has to be an accurate physical and visual representation of the cockpit. Everything has to work in the way that it does on the aircraft to avoid any negative training by getting familiar with the simulator and finding the aircraft is different. The flight deck, you'll have in there the flight controls, which control the surfaces of the aircraft. On the Boeing, it's a yoke, which is the column and wheel that we all sort of do when we're pretending we're flying an aircraft. And on Airbus, it's a little joystick. There's a joystick either side that the pilots use to fly it. There's a visual system fitted on the front. I'll say more about that later, to give you the out of the window view. and a projection system to produce that picture. There's, I don't know how you go back with this, the motion system. I will get onto this, which is the legs that it sits on. I'll talk more about that later. A sound system to give you all of the sounds of the aircraft, environmental sounds, aerodynamic sounds as you're running it. There's an instructor operating station which allows the training pilot who's sitting behind the actual trainees to control the exercise that they're going through, so he can make them fly different places. He can put malfunctions on, so for example he can make an engine fail just after takeoff, he can make something happen at a certain altitude, many different things. And when one of these simulators is sold, the customer will take a standard set of malfunctions that he has to have for training, and then a selection from, there's usually a library of hundreds of malfunctions that they can choose maybe 200 from, to put on their simulator for the instructor to use to vary the exercises for the pilots going through there. Because every pilot that's all qualified has to have a check flight every year on a simulator where they can put it through his paces, check that he's still flying properly. And finally, all of that lot's controlled by, surprise, by a computer system. Now, I'll get onto that a little bit later as well.
Well, I'll just ask, Jeremy.
Yes.
You say you specify up to 200 sort of special events out of a long list.
Yeah, I mean, it depends on the aircraft type, but over time, more and more of these malfunctions get developed and integrated into. You've probably got a list of 300 to 500 of them, and a typical one will be delivered with somewhere between 100 and 200 of them.
For the pilot, but the simulator itself has got all 500 in there capable, or not?
They'll all be built into it, yes.
Yes, okay.
But what will happen, the customer will choose them, and when I get onto the instructor station, you'll see there will be pages that he can press buttons on to select the malfunctions. So you'll set him up with maybe 10 pages of 12 malfunctions on each, grouped together by classification, but they will be out of the 300 or whatever the software is capable of modelling.
Yeah.
Okay, the flight deck. This is the flight deck of a 787 Dreamliner. As I said, everything is full physical facsimile of the aircraft. Basically, everything from just behind the pilot's seats forward is exactly as per the aircraft, so that they don't get any false training from it being different. The 787 has a head-up display for each pilot. So that's just a picture of it over there. So within the cockpit there's the model of all of the avionics, flight management computer, navigation aids, traffic collision avoidance, ground proximity warning, weather radar, comms, all of that lot is on there. Models the autopilot and the auto throttle. Landing gear, can't quite see it, where is it? It's somewhere. Put it the wrong way around, there we go. Somewhere around here you've got the landing lever, which is still a clunky thing on a Boeing, even though it probably doesn't really need to be anymore. The head-up displays, as I said, there's one there, and that's what they look like closer up. And the flight controls are going to do another slide. Now, as time has gone on, these have got more and more complicated, as you can imagine. The avionics on a 787, all of these boxes are networked together. There's quite a complex networking system between these. And I'll get onto a different slide about what we put in and how we deal with that. In fact, which is it, the flight deck. Simulation versus stimulation. Back in the day where the old aircraft had dials and knobs and switches and things like that, there was quite often we would simulate them. We'd use meters and dials and knobs that looked like the real thing, acted like the real thing, but actually were cheap copies. The reason being, using aircraft equipment is 100% accurate but very expensive. All of these bits that go into an aircraft cockpit, a real aircraft cockpit, are obviously graded to a very high level of reliability and very long mean time between failures, and for that reason they're very expensive. The downside of it, perhaps, it's difficult to interface to the host computing system. That on the 787 there's a rack of this sort of size of networking hubs to connect all the bits together. can be difficult to stimulate. So, for example, the flight management computer, usually you'll put in your position, your route, and it will fly it, and it will go happily along as you fly the real aircraft. On a simulator, you might want to take off from Gatwick, so you start at Gatwick, finish that 10 minutes of taking off or whatever you do, and you want to be in Singapore. So you need to put the whole thing into Singapore, a reposition as we call it. And the flight management computer can get upset about that. So there's certain ways that we have to do it to override that. The pros of the simulated ones, as I said, they're cheaper to manufacture. They don't need airworthiness certification. They're difficult to ensure they're an accurate replica if the drawings aren't available. And this is the one that really makes those difficult. You have to continuously monitor and update changes. If the real aircraft bit changes, they've got to make sure the simulated instrument keeps step with it. Flight controls. Okay, as I said, there's a side stick for Airbus and the wheel and column for Boeing. And they have to be identical. The column has to feel as if it's on the real aircraft. Accurate force feedback to replicate the actual aircraft, and a stick shaker on Boeing, so if the aircraft gets to too high an attitude and it thinks it's going to stall, it shakes the stick to give you a warning that that's about to happen. And with the column on the Boeing aircraft, the real irony of that is now we've spent years and years developing the feel and the force feedback on that to make it realistic like the aircraft, to simulate the feel of the old wires and bits and cables that used to operate the levers. The 787 and most of the modern aircraft are now fly-by-wire. So this, in the real aircraft, is a simulation of a column to provide the signal to drive the electronics. So it's almost like a simulator into the real aircraft. So that's the irony of that one. Pitch trim is another important one. It's called stab trim on Boeing and it's called the THS on Airbus, but this is the trim, which is the horizontal surface in the tail section to alter and trim the pitch of the aircraft. The visual system, right, so consists of an image generator and a display system. The image generator generates out the window view for various conditions. Nowadays, most of them are real-world view, Google Earth type quality of texture. You can sit on the simulation, you can fly over your house and you say, oh, there it is down there. It's that good now. When I first joined back in '87, the visual was, well, they just stopped using the model boards, which would be a little camera going over a real physical model board about half the size of this wall. But the electronic visual systems back then were very crude. If you flew over a forest area, it would be green like a billiard table and some little triangular trees with brown stalks on it. And that was about the level of fidelity that it was back then. So as you can imagine, it's moved on quite a lot since then. And that brings me to the point that I retired in 2020. The technology will have moved on since then. But I can comment on what it was at that time. Having said that the technology's moved on, the main components of a flight simulator won't have changed much. It's just that the technology moves on as you go along. This out the window view gives you pretty much, you can fly almost anywhere in the world and have a good view down below you or whatever. But for the airports themselves, there's a much higher definition airport model so that all of the buildings are modelled and textured. They're modelled as 3D blocks that you can drive around while you're taxiing around the aircraft, around the airport. All of the runways are modelled very accurately, and there's a process we go through when setting all of this up to get them aligned geographically, because sometimes the models don't quite fit, and we have to make sure that the runways are in the correct orientation for approaches and landings and takeoffs. Visual systems used for a few other non-simulation things. So, well, it's part of simulation. Typically, if you actually crash the simulator, it flashes the screen red at you, and just so if you hadn't already noticed that you've crashed, it warns you of that. It provides calibration programs that the visual system, integrating the visual system and the proper display, which I'll get onto in a minute, needs calibration and setting up. Ray at the back there can tell you far more about it than I ever could. But you need patterns to You'll see why in a minute. And it also provides terrain elevation data. So as you move over, the simulation tells the visual system where you are in the world, and the visual system tells you the terrain elevation at the point where you are. That's the default way of operating. There are other ways of doing it, but that's the normal way that the system operates. So the visual system has within it a model of the Earth in 3D to give you that terrain information. The display system, I'll look at some more pictures of this in a minute. These days, they might have gone up a little bit, but typically 200, 225 degrees horizontal and about 45 degrees vertical. They can be bigger than that for military simulators, but this is the sort of size that you'll get for a commercial aircraft. And the vertical is usually goes up 15 because you've only got a bit of sky above you, which you're not much interested in, down 30 so you can see the ground in front of you when you're taxiing and on the ground. And real and virtual images, I'll tell you a bit about that next. And Ray will tell me if I'm wrong. Okay, collimation. For commercial simulators, we have to have a collimated visual display. What does that mean? I'll tell you a bit more about it in a minute, but real images versus... So, to produce a collimated display, you have a projector, you have a screen that you project onto, and your viewer looks at the image of that in a mirror, a spherical mirror, a section of a spherical mirror. What does that do for you? It means that the light from the image hits your eye and the light is parallel. And that means that effectively it's coming from an infinite distance. Anything at infinity, light is hitting you parallel. Something close by is diverging as it leaves you. That's important for commercial flight simulators because you've got two pilots. And if I could just stand here for a moment and show you what's wrong with that's a real image because it's projected onto a screen. And let's say that bit there is the end of the road. Now with that real image, if I'm the pilot this side, I'm looking at it to my right. If I'm the pilot this side, I'm looking to my left. Not like the real world, both of them are looking straight from the end. Now with a positive display system, the pictures are so those two are definitely going out. So that's important for it, and this is a different kind of how it works with the decoration and the icons. It's not quite a perfect system. As I say, they can tell you far more about this than I ever do, but it's like most engineering things, it's compromised because the icon should be in the centre of the curve with the mirror is not square. So the image is not quite as perfect as it should be, but it's good enough. And although I said it's focused at infinity, if you actually measure it, the image is typically about 10 to 15 metres away, but it's like far enough away for it not to give you the problem parallax effect that you do with a real image. So that's what that has in there. And because that's important to the training of pilots, all level D simulators have to have a collimated display. And this is different from military simulators. Very often with military simulators they do have a real image because you've got one pilot, one eye point. Doesn't matter, you don't have to have this separation of two pilots. So you saw the outside of one. This is sort of a bit of a cut-through view of it. So the projectors will be sitting up on the top of the simulator somewhere. There will be the curved screen. Actually, it's a bit more curved that way there, but the projector will project onto the back of that. A sort of looks a bit like frosted glass, but actually the image that is produced by it is very sharp. It doesn't actually appear frosted, but the mirror surface obviously has something that the light could land on. And then the pilots will sit here, and you with a mirror that's sitting in front of them. And that's the sort of physical layout, projector, screen, mirror, and that is one of the mirrors. And it's, what radius are they? About 5 metres, are they, Ray? Something like that?
I tend to think that in feet still, so there's 10-foot radius, 11-foot radius.
Okay, so probably about 3 metre, 3 and a bit metre radius. But this piece here would probably be sort of like from that point there round to here, that it would curve around the cockpit as a large unit. And it's basically a glass fibre structure, hollow structure, with mylar film over it, which is only about 1 thou thick or something like that, and it's sucked back under a vacuum, which gives it the smooth, curved surface. So when the simulator's not in use and the vacuum system is off, that just looks like a piece of baggy foil. And when you start the simulator, it gets drawn back into position, and it's maintained at the right length with a ultrasonic sensor, so it doesn't get overdrawn, and it is drawn back enough. Okay, so there's the Air France again. So the motion system that I mentioned earlier, there's 6 legs underneath it supporting this, and it provides 6 degrees of freedom. So the aircraft has 6 degrees of freedom, 3 translational ones. So if that's the aircraft, surge is in the axis of the aircraft, heave is up and down, and sway is side to side. So those are the 3 translational axes. And then the angular axes are pitch, roll, and yaw. So those are the 6 degrees of freedom. And having these 6 legs here, by a clever combination of all of them, you can produce each of those degrees of freedom independently or in combination. And the maths that goes behind producing that is far beyond my level of maths, but there's some very clever people that do all of that to make sure all the legs go in the right place at the right time. Now, the interesting thing about it, if you're not familiar with flight simulation, is the purpose of the motion system. A lot of people will assume that if the motion system's like that, you're taking off, and if it's like that, you're landing. That's probably true to an extent, but not totally true. It's to produce acceleration cues, not to show the attitude of the aircraft. So during takeoff, when it's like that, what it's actually doing, if you're actually inside the aircraft, you've probably just put thrust on, and what you see visually is you're going along the runway horizontally. But it tips you back like that to give you the push in the back of your seat to make you feel you're accelerating. Similarly, when you see it like that, it's probably just touched down, and you're applying the back reverse thrust and the brakes, so it's tilting you back, tilting you the other way, forwards, as if you're braking and decelerating. So it's acceleration cues, not the attitude of the aircraft, although it corresponds to a certain degree, but it isn't actually what it's there for. Apart from providing those, it can do vibration, so you've always got engine vibration as you go along, aerodynamic noises, so buffet, things like that, impacts if you actually hit something, upsets, again with, I said turbulence there, microbursts, wind shear and things like that throw you around. It also does some special effects for some of the malfunctions. For example, if you want to do a fairly serious malfunction, you can do an engine separation. Engine drops off. Obviously, when an engine drops off, that's a heavy piece of kit, and you said the aircraft's going to do a lurch till it recovers from it, so it can use motion cues to make you realise that that's happening. The sound system. Typically, there's a multi-channel sound system. It'll have, I'm trying to think how many channels, probably 6 or 8 channels. There are speakers above the top of the cockpit, there are speakers below to the sides, speakers below, woofers down below to give a rumble and things. It's a multi-channel surround sound system, and it does all of the aerodynamic sounds of wind, hail, things like that. Aerodynamic sounds, wind sounds, engine sounds, and turbines, and stalls. If the engine stalls, it gives a thump, a bang. Environment sounds like hail and rain. It'll give you those sounds. Attitudes, alerts and warnings. So things like if the autopilot disconnects, there's a whoop, whoop, whoop noise goes off. Engine fires, which is typically a bell sound. It'll simulate all of those. It'll provide the GPS warnings. When you get too close to the terrain, it tells you to pull up, things like that. Traffic collision avoidance. It'll warn you if there's traffic. If it gets too close and there's a impending collision, it'll tell you to climb or to descend. I have to say I'm really not quite sure how the two talk to each other, because it'll be telling the other one to go the other way, you hope. But those that know about it know how it works. Special effects decompression, terrain if you're just running over a lot of rough terrain, or tyre squeal if you try to do too sharp a turn and the tiller wheel, the nose wheel, is sliding horizontally, you get wheel squeal and judder. It also provides automatic traffic information system. This is created system that comes from the control tower and tells you which runway conditions are, what the weather is, what the equipment status, like if the approach radar or approach system is out of order. And it also, through the sound system, you get crew communications. So each of the pilots are connected in with a set of headphones. They can talk to each other. They can talk over radios to the ATC. And for talking to the ATC, the instructor sitting behind can actually act, if he wants to talk back to them as the traffic controller. So those,
Just ask, decompression.
yes.
Do you actually reduce the pressure in the cockpit?
No.
All right.
No, not that I know of, unless the technology has moved on that much. But no, I mean, that one really is too difficult to do. But we do the sound and the sound of escaping air as much as you can do without actually decompressing.
You get the odd scream from an air hostess? Or?
Well, that could be added, but I don't think we've got it yet. One of the other extra bits and pieces which I haven't mentioned on here, now that you've said about that one, quite often they have smoke simulation on the sim. So if there's a electrical fire in the cockpit, you can fill the cockpit with smoke, which makes it, yeah. It's a smoke generator, non-toxic smoke, obviously, but it's so you can't see what you're doing very easily. So that can be done as well. Not all simulators have it. It's one of the optional extras that you can have if you want with your simulator. The instructor operating system I mentioned. This is a typical sort of arrangement, but there are many different ones. A seat for the instructor and a screen or two screens. And down here you probably have what have I got, comm box? Should have a comms box somewhere. Oh, it's just showing some of the mechanical bits, but usually there's a comms box on there, which is the same as the comms box that are in the cockpit, so that he can talk to them as ATC if he wants to do that. That allows the instructor to set up the training scenario that he wants to do, starting with an aircraft configuration. Now, some of these can be done as presets, but he can set up the zero fuel weight, the amount of fuel that he wants, and the cargo, and he can set where that is, so that the centre of gravity is at a certain point in the aircraft, depending on where your cargo load, or to simulate passengers down the back. Knowing where the centre of gravity is important to the pilot, because he'll need to set the trim correctly for takeoff, using the settings on the control column, on the control in the middle. He can set up departure, airport, gate, taxi and hold positions. So he might want to decide that you're going to go from Gatwick and you're going to leave at gate 57. I don't know what numbers they have over there. If he does that, it'll position the aircraft at that point. And then there's a process that the pilots have to do with the brakes and things to release it so that they can do the pushback to take them out to taxi to the runway. And that's one of the things that we had to do when we set up, one of the customers' options are the airports that they want, because obviously not every customer will fly from the same airports. So they, as part of their thing, typically, like I mentioned about the subset of malfunctions, they will typically have 20 or 25 airports that they're interested in, and they will have those high detailed models of those aircraft, and we would set them up with properly aligned pushbacks for the gates that they use to take them, depending on where physically it is in relation to the taxiways. You could do a taxi push back left, tail left, tail right, and push back straight. Just depends on what's behind you and where you're going to taxi out of. So some gates you only have one possible pushback. Some of them you can have two, some of them you can have three. And some of them go a very long way. You're sort of going like this to get out to the taxi point. So he says that that's the initial position. Or he may say, okay, we don't want to do all the pushbacks and that. We'll put them at the hold point, ready to be clear to go onto the runway and take off. Or you can actually put him on the takeoff point straight away. You can set up environmental things like time of day, level of precipitation. You can have it on a rainy day or snow even. We do snow on the visual system. Set up the visibility and set up wind. So if you want him to take off with a bit of crosswind, you can put that in. you can set a destination airport, and then the malfunctions that I mentioned, you can either put them on, just physically it's on or it's off, or you can arm them. So you could, for example, say, I want this engine to flame out when we get to a height of 200 feet, and that's what it will do automatically. You don't have to remember to do it at that point. And there are, for commercial aircraft, they have lesson plans, which is a sort of profile to do a basic, you'll do a takeoff, a climb, a bit of cruising, a descent, approach and landing, and it provides a way of guiding them through that without too much instructor interaction. So it just makes the instructor's job easier to run through a repeatable scenario. So this is typical of the sort of pages that you might have on here. So here's one there, it's setting the takeoff airport at, what's that? That's Amsterdam. Gate numbers. And these are, so that's the airport, but these are in-air repositions that you can do. So apart from being at the takeoff point or at the hold point, you can actually position him coming in from the left, coming in from the right, on the final approach at various distances. So if you just want him to practice a landing, you could say you come in here and land, or come direct in. This is a typical configuration one where you're setting up the fuel level. So you can put total fuel in. If you put total fuel in, there's an algorithm that decides what it puts where. Typically, it will fill the wing tanks first. Then if you add even more fuel, it will fill the center tank. But you can, as you can see there, you can specify them individually if you want to. You can set the gross weight, the center of gravity of the aircraft to simulate, where the cargo or passengers are in there, and to make sure that the pilot sets the correct trim for takeoff. And you can set fuel temperature so that it's not too low. What we got here, and then the computer system drives all of this. It has interfaces to all of those various pieces of equipment. When I left, this was where it was at. It was a PowerPC based unit, 0.5U, which is about 4 inches in a 19-inch rack, and that one computer could drive most of the Airbus aircraft. It could do 737. The 787 was so much of a beast it needed 2 of them. We actually needed 1 1/3, but it had to be 2 boxes basically. But again, since the time I joined the company, when I joined in '87, the computing was a mini computer that came in a box sort of this size. Didn't have a lot of memory. Disk drives back then. I was working on the Harrier when I first started there, and for the main storage they had 300 megabyte drives, which was big for the time, but it was the size of a washing machine and cost about 10 grand. And for that particular one, for the 787, for the Harrier, they wanted to have a feature called record replay, where you'd fly the simulator and it would record it. And then when the top brass came along, you sat in there and they played it back. So they used to, you could fly it through the valleys of Wales, perfect flight, and then you'd play it back for the top brass. And for that, they needed a much bigger disk drive. It was a 780 megabyte, which is almost unheard of at the time. Again, size of a washing machine, and I can't remember how many, but thousands, absolutely thousands of pounds. And I remember a bit later on, probably a few years after, so probably about early 90s, we did a simulator for the Augusta 129 attack helicopter, and it had 2 cockpits on motion systems, one simulating the pilot and one simulating the navigator gunner. And that, on the aircraft, they sit like this, one above the other, to reduce the forward visibility of it, for opponents to be able to, not so much of an aircraft to aim at. But these could operate integrated, so the pilot here and the navigator were in the same simulation, or you could separate them, and they did separate training exercises. And to run that again, it was mini computers, but it had, I've forgotten how many of them, about a dozen of them interlinked with a high-speed memory bus between them. And it also, because it was a helicopter, it had a blade element theory model. So instead of it just being like a disc, it was each of the blades had elements along them, so it could start to do this and that as it got force on it. And they were modelled by four. Each of the rotors had their own mini computer. So this whole thing was a complex beast. And I can remember raising the purchase requisition for this computer system. And back in whenever it was 92, I think it was $1.6 million. So things have moved on. These boxes cost about £2,000, I think. So what's in there? Flight simulation software. Okay, so it's frame-based, so it runs the same programs over and over again at a repeated rate. And at the time I was there, 60 hertz was the standard. They always want to get it faster if they can because it reduces the latency. Obviously, anything that comes in as a stimulus has to go through these before it comes out as an action. So the faster you can get the thing running, the lower the latency. But 60 hertz was the standard for commercial simulators when I left. They were thinking of getting up to about 100. Some of the military ones get at 100 because they maneuver very quickly. So you really do need extremely low latency. So it wouldn't surprise me, although I've got no information, it wouldn't surprise me if they pushed that up to 100 by now. So basically, everything, the critical loop is from pilot input on the control column or the stick to the aircraft responding. And that's the critical loop because that's the most noticeable effect. Now, there's an interesting thing about that, which is that in getting the response coming out, you have to get the right sequencing of the motion system and the visual system. Because if you get it the wrong way around, you get sick. And basically, the stimulus, and there's not much time between them, probably one frame or even less than that, but you have to move the motion system first and then the visual system. And if you think about it, that's exactly how it works. If you're in your car and you put your foot down, you feel a bit of oomph before you actually start noticing any change in the thing. And there's that sort of built-in inertia, if you like. It's simulating the inertia, I suppose, really. But if you get it the wrong way around, it can apparently can make you sick. It's probably what these amusement rides do, where they just throw you around and they probably don't care much about which goes first. Anyway, so that's the critical loop. So that all of the tight bits there run at that frequency, and other things like, I don't know, some knobs and switches. Probably, you know, if you've got a couple of hundred milliseconds delay, you probably never notice. So they can run at a fraction. This frame-based scheduler runs things at full rate, 60 hertz, half rate, 30 hertz, and so on, down to very, very slow bits for things that don't matter. And the bits of software that are run at different rates are jiggled around to try to balance it so that each of the frames of the 60 hertz have the same amount of processing in as near as you can get it. I mean, obviously some you can't do that with, but it's trying to balance it out. So what goes on in there in those calculations? The critical loop that I just mentioned was a stimulus to equations of motion. Equations of motion are, to say the least, complex and far beyond my maths, but basically, in a simplistic way, equations of motion, it's a double integration. You work out the thrust from the engines, you work out the lift from the wings, the drag from the air, the turning motions from the weights and the centre of gravity, and you solve all of those in real time in this 60 hertz thing, and then that gives you, that works out all your forces. And from the weight, you can work out the acceleration on the aircraft in all of its different axes. You integrate that and you can get its velocity. And you integrate it again, you get its position. So it basically, double integration works out how what the equations of motions are doing. That's a very simplistic view of it, and it's quite complicated to do and far beyond me, but that's in a nutshell how it works. Obviously, these are all done at that rate to make sure everything goes on, because there's equations of motion. Weights and balance, obviously, as you use fuel, the weight changes depending on which tank it's coming out of. The centre of gravity may change, so all of your moments and things like that may change as well. And there are ground effects as well when you're actually taxiing and close to the ground. That's the sort of standard stuff. Then there's other components. So some of the bits in there, we've taken real aircraft software and retargeted it and run it in that host computer. So some of the parts of the 787 software actually run. Some of the real software components are recompiled and shoved into the host computer of this. One of the other things that goes in there when we can, it's SimSoft. I mentioned to you earlier that the flight computer doesn't like it very much when you try to move it around the world rather rapidly. SimSoft is a sort of interface, a sort of under the hood interface that allows you to get in there and force the changes in. And that's implemented to various degrees by the aircraft manufacturer. The problem with that is it's needed for simulation to make it viable to do repositions. The aircraft software obviously has to be high reliability, very trustworthy. They don't like sticking in bits that aren't really there for the aircraft. So it's a bit of a hot potato really, but you almost can't make simulation with the complicated boxes that you've got on something like a 787. You can't really make it work without some element of SimSoft, so there's some of that in there. Then there's interfaces to the avionics network itself. I mentioned that a lot of the boxes in the aircraft are networked together. And this comes back to the comment I made earlier about stimulation versus simulation. These sort of things, they're too complicated to simulate completely. So a lot of these physical boxes are the real aircraft parts, which again, because I mentioned earlier, they're very expensive. But typically when we did a 787, we'd buy a kit of aircraft parts from Boeing. And before you got started, that was $1 million to get going with. In fact, it might have been £1 million, I can't remember. This particular box, this ISS, it's integrated surveillance system. And it's a box about like that holds the weather radar, the ground proximity warning system, and the traffic collision avoidance. And that box alone is $250,000. Visual interface, okay, so the visual system that we're talking about, the simulation has to tell the visual system where you are in the world, and the interface for that is typically Ethernet. We've had other different ones in the past, but Ethernet seems to be the standard now. And the motion interface these days is Ethernet. It used to be some sort of parallel interface way back in the day, but Ethernet works very well for that. And then the I/O for linkage. There is still an element of physical linkage with digital inputs and analog inputs and so on, and they're usually connected. Well, they're connected to a controller via Ethernet. There's less linkage, as we would have called it now, but in the days of the old simulated instruments, you'd have analog outputs driving the meters and dials, and you'd have digital inputs on the switches and things like that. A lot of that comes in over the computer network from the real boxes now. And oh yeah, and there's a separate management computer. So this is the host computer running the scheduler at 60 hertz, and then there's a separate management computer. It's basically a top-end PC or high-end PC that actually the operator loads the simulator from there. Says, I want to load this simulator, I want to start on this position or whatever it is. And also for background and all sorts of housekeeping, like keeping records, recording information, that sort of stuff. It's a separate computer. Certification. I mentioned earlier that these are level D devices, which means they're zero flight time training, sorry. And obviously, if you're going to train the pilot in that and then let him go on a real aircraft straight away, it needs to be a high level of quality and training. So no simulator, unless it's certified by an approving body. For the UK, it's obviously the Civil Aviation Authority. For America, it's the FAA. And most countries around the world, or many of the countries around the world, have their own. So the Chinese have CAAC, which is the Civil Aviation Authority of China, and so on. France has DGCA, which I can't remember what it stands for, Director General something or other. But some countries don't have their own approving bodies, and then the FAA or CAA might certify them on their behalf. And they would work under the umbrella of this European Safety Agency. So that's the UK, that's America. And the CAA often act in that role of being one of those for countries that don't have their own local approving body. Right, the system certification has two elements, a subjective and objective. So the subjective, and this approval process usually takes of the order of a week or so. So the subjective bit is that experienced pilots and instructors would fly the simulator, run not necessarily proper exercises, but just to give it a fly around and say, yeah, that feels right, it's doing the right things. They'll try some performance handling and malfunctions. They'll check out to make sure the avionics works, which are things like ground proximity warnings and traffic warnings. And they'll just check out a subset of the instructor facilities, make sure it's got all the things that they think it's going to do. The objective assessment is called the qualification test drive, and it measures the aircraft performance and ground handling, all these different things here. And there are a set of little tests, each of them probably only sort of a minute or half a minute long or something, where it will stimulate the aircraft software and look at the responses that are coming out. So, for example, it will put the thrust to full and measure that you're getting the right amount of thrust. It will, I can't remember all the different things. It'll check braking, for example. When you touch down and put the braking on, it'll check that, and it'll check braking. It's basically setting it up like the instructor could do, but it's all doing automatically. These tests are coded in a sort of pseudo language that says do this, do this, do that. And for example, it could set up an aborted takeoff. So you run up and abort at the V1 point and slam the brakes on, and it would see how long it takes you to stop. Then it might try it again with a wet runway, and it'll produce all these graphs and things, and they're compared against a set of test results that have come from the aircraft manufacturer for the real aircraft, and they have to be within a certain percentage of those to pass the test. I think it's fairly small, like about 3% or something like that. There have to be quite a close match. And they check all of those sort of handlings. They check sound in different... That's a little bit of a strange thing, because I think it only really it has a microphone. It only really measures the sound level. So, I mean, you hope that when you're roaring the engines up, it sounds like an engine, but if it just made some large, loud noise, it just might pass the test. I'm not sure about that, but I don't think it does a full frequency analysis and anything quite as clever as that. But it does, again, they will have sound levels from the real aircraft, and it has to match within a certain level to make sure of that. And the difficult one always seems to be the quiet cockpit. Everything's off. Obviously on the real aircraft it's quiet. And there's usually something making a noise on this, whether it's an amplifier in the motion system or a control system or something, and it produces a little spike on the spectrum that they don't like. You have to check the visual and motion latency. I mentioned the critical loop and the response from when you push the column, and it measures those as well. So it will provide a stimulus into the column, for example, and you'll see the column move forward. There'll be an accelerometer underneath the floor, which will check when the motion system goes and measure the time on that. And there will be a little test pattern that it can put onto the visual system with a sensor of some sort. I can't remember quite how it does it. It's a little photosensor points at a white square or something. And then when you put the stimulus in, that white square disappears, and it obviously measures the time for that to check that it's within tolerance for latency and that the motion cue is ahead of the visual cue, as I also mentioned earlier. And then, as I said, finally, they're all plotted against real aircraft data for analysis, and the customer's approval body, the CAA or whoever it is, together with the customer themselves, will go through all of this detail. And typically that process, that part there, takes 2 or 3 days. This doesn't have to be all at the same time, but typically it's a couple of days of flying out for getting the subjective assessments. And then at the end, if that passes all the approvals, then the simulator is approved for training, and the customer can start using it. These certifications are slightly strange, this one in particular, in that although we would put the simulator together, we would assist the customer to do all this, but it's actually the customer's responsibility to get it approved with the approving body. So we support them in doing that, but we don't offer it to them. They do. But it ends up that we're doing it basically anyway. Optional extras. Well, I mentioned the smoke one, which I don't think I put up here. Brief and debrief. Briefing is unique to a 787. It's a classroom-based thing. And basically, it's a PC, and it's got a full... It's connected to a single computing bit that has the full simulation of the aircraft in there, but produces it on a screen as a virtual cockpit, and you can, with a cursor, a mouse or something, you can click the knobs and switches and you can make everything happen and things light up and do it just as they would. So you could practice starting up the cockpit, for example, without using up the main simulator time. You do all the basic training in one of these. The other system that we offer is a debriefing system to maximise the full flight simulator time. So there's a camera and microphone that records the pilots, so you can see how they're interacting. The instructor, if he's going to debrief them afterwards, can put on the instructor station, press a button to say, put a marker here, because I'm going to come back to that when I talk to them afterwards. And all the switches that they play with on there are time-stamped, so they know exactly what they pressed at what time. And that's all recorded during the running of the exercise. They finish their exercise, clear off, next lot can get in, because obviously simulator time is at a premium, so you don't want them sitting there talking about it. They can then go back to the classroom, and it's like a video style playback, you know, fast forward, play, pause and stuff like that, plus these timestamps, so the instructor can debrief them on, you did this here, you actually should have done this or whatever, and on the camera there, you were doing that, you should have been talking to your colleague and checking the checklist, or you know, all that sort of stuff. They can do it outside of the simulator, and as I say, it maximises the simulator time. This was being prototyped as I left. Just shortly before I left, we were supplying a simulator to Qantas in Australia, and we were working with an Australian company on a system that would do pilot eye tracking. It was a harmless infrared scanning thing, and it wasn't perfected. They were still prototyping it then, but the idea was that along with all this sort of stuff for debriefing, it would actually say, look, you were doing that, you were looking over there, why were you not looking at that bit? You know, and they could actually see where his eye point was rather than just looking at where his head was. So so that's a new thing that was coming in. They might have done that by now, but that was being prototyped at the time that I was working there. That's it in a nutshell, but if you have any questions. Yes?
Yeah, when you mentioned to simulate the acceleration by actually tilting the simulator physically
Yeah.
away, presumably the pilot's view out the view screen doesn't move, it still looks straight down the runway.
That's right.
Yeah.
So you're sitting in the cockpit, you're looking at the end of the runway there, you're at the takeoff piano keys, you put the thrust on, and you're going straight along the runway till you reach the rotation point. You're going straight along there, but what's happening outside is the motion system's doing that to push you in the back of your seat, so you think you got some thrust. And the visual stimulus is very powerful. You don't, because you're seeing a picture straight in front of you, you don't actually you don't sense that you're being tipped up. All you feel is something in your back. It's very clever.
Next question.
I was interested, you mentioned a menu essentially of choices of simulation that can be generated, which the customer chooses from to be fitted to his simulator, so that the instructor can choose from.
Oh, for the malfunctions, do you mean?
Yeah.
Yes.
Yeah. There's does anybody specify what is required for the pilot to have gone through
Yes.
before he gets certified?
Some of those malfunctions are optional extras, and some are the ones that are related directly to the quick reference manual that he will follow in the event of one of those malfunctions.
Yeah, but is there a minimum set that he
Yes.
must go through?
Yeah, he will always have that minimum set, and then he has options of the extras, because the aircraft manufacturer will produce, I don't know what it's called on Airbus, but on Boeing it's the QRM, Quick Reference Manual, and if suddenly, for example, suppose one engine suddenly drops out in flight, he will go to the quick reference manual, check this, check that, check. It's a quick finding route.
Is that set of minimum set specified by the customer, the
aircraft manufacturer, the manufacturer.
or a separate certification board?
It will be the manufacturer. For example, for the 787, Boeing will provide a list of malfunctions that they will give you support for.
Independent of Boeing does that.
Not that I'm aware of, but it's possible, but I don't think so.
The back row first.
Right.
Could you say something about the role of the simulator in the development of new aircraft types? For instance, how soon does the aircraft company and the simulator company start talking to you?
Well, that's an interesting one because generally the simulator is produced from a set of initial data. In the case of the 787, that was a very interesting one. The very first simulator, we produced 8 simulators for Boeing. And the very first one was called the JUS, which stood for Joint Use Simulator. And it was used by us to develop the simulator, and Boeing used it for doing engineering evaluations and trials. So yes, we did, and that one in particular, we got involved with Boeing very early, long before the aircraft was flying. And we did the site acceptance of it, actually at Gatwick, at their training facility at Gatwick, and I did the acceptance there. And we did that before the first aircraft had even flown.
So the simulator results can feed back into the aircraft design process, presumably?
They can, although it was intended that they'd use it for engineering work, I don't think they did a lot of it. But we worked on developing the simulator with them, with a lot of input from them while they were developing the aircraft.
Mike?
Yeah, a question about military aircraft now.
Yes?
Different characteristics. For instance, a fighter can go straight up.
Yep.
When you simulate that, does the whole screen go vertical, or what happens?
The visual system will, yes. But this is, I mentioned display systems on military aircraft tend not to have a collimated display because you've got one pilot, so you have a real image display. And it can be a flat thing, or, I mean, some of them have a dome with an absolutely enormous field of view, but it's a single eye point. It's not a collimated display. But the other thing there is for sustained G, which you'll get if you're going up like that. The limitation on these motion systems is those legs can only go about 1.5 meters or something. So if you're going to give some acceleration, you're going to run out of legs sooner or later. So you can't give never-ending acceleration cues. So they're not suitable for military aircraft. So they usually don't have a motion system. And what they tend to have is what's called a G seat, which is a seat with some straps. And when you want to simulate them actually getting G-force, it pulls on the straps and pushes on you, just like put some force. Yes.
Then the horizon doesn't have to move.
Well,
If you want a G, sustained G, you could have the simulator on the end of a rotating arm. Well, maybe someone, I think they do subject pilots to that sort of G.
for military, they probably do. They wouldn't do it for commercial aircraft. It would be,
No, not commercial.
no, it'd be a horrendous thing to try to do anyway. No, but yeah.
Different question. The TCAS, the Traffic Collision Avoidance System.
Yes.
I believe from a pilot friend that you have to set it up on the ground. You have to set it up for, the parameters in that, because on one occasion, because I had one of these SBS type flight radar 24 type ADS-B type system, and I recorded an aircraft, instead of landing on the runway in Gatwick, landing in the middle of Crawley, because the TCAS ADS-B system had, so I was told by my pilot friend, had been set up incorrectly in America or something, or so the whole there is a fault, and I wondered if that kind of thing. I mean, the other thing with TCAS is that sometimes the order from the TCAS equipment conflicts with either common sense or with what the air traffic controller might say. Are those the kind of things which
Taking that last point first, you're quite right. And I like watching air crash investigation, and there have been cases on there where the pilots have got confused because TCAS is telling them one thing and the air traffic control is telling them the other. And depending on which airline it was, some of them say air traffic control is God and some say TCAS is God. So
it's not resolved?
I don't know, it might have been now, but this was quite a long time ago.
Resolved now. There's a crash over Germany between a Russian aircraft and I can't remember what the nationality of the other one was. It was European, and basically one followed air traffic and the other followed.
Yes, I think that was probably the one I saw on there.
And they hit each other.
Obviously very rare, but yes, it does happen. But I don't know.
The rule is
Yeah.
TCAS wins.
Okay.
You follow TCAS and then you're deemed to have acted for the safety of your aircraft.
That makes a lot of sense because TCAS knows where the other one is and should, as I said earlier, should tell you to do that.
Well, if you do the wrong thing, the other one to do the other thing because it can reverse its decision.
Yeah.
So hopefully.
Hopefully between them they sort it out, yes.
Yeah.
But that, yes, you're quite right about that. The first point you made about setting up the TCAS, I'm not aware of anything you need to set up before you leave the ground. It's automatic. So I'm not quite sure about that. I do know, yes, that you can get the wrong information.
Recording if you,
No, I don't disbelieve you. And the ADSB stuff, yeah, I'm not sure where that comes from. Yes, that was something I didn't get fully involved with. So I'm not sure is the answer to that. But as far as I'm aware, I'm not aware of any process that you do to set up the TCAS before you depart.
well, I'll check with my pilot friend.
I would have thought any information it got would have been from the flight management computer that you set up. Yes, right, Mike.
A question about faults when they occur in the simulator. What does it do to the pilot? I mean, do they think it's a real fault, oh my God, what should I do? Or do they break off and say, this looks like a simulator fault, we better get on to Charlie's or something?
Oh, a simulator rather than a malfunction of a model, rather than a model's
So
malfunction.
your-
A fault in the simulator.
your apparatus, yes. How often does it happen?
Once it's been through its acceptance and certification, not very often, I have to say.
But sometimes.
Well, something can always slip through its software, isn't it? You know.
Yeah.
But if it interferes with the training scenario, they will probably try to work around it if they can and just do something slightly different and report the fault. If it's something that stops it dead and is effectively called AOG, aircraft on ground, they use the same term for the simulator, it gets priority addressing from us. Well, from us, I don't work there anymore, but yeah, from the manufacturer, simulator manufacturer. But yes, it does depend on the severity of it. If it really means that they cannot train anymore, then it gets a very high priority. Probably send someone on the next plane out there to go and sort it. Yes?
The question on software updates, obviously the whole thing runs on software. You have to update that, and you mentioned about changes to the real-life instruments have to then be simulated. You've got to go around and do an upgrade on a simulator, presumably. How long does that take, and what's the sort of process, and do you then have to recertify after that?
Take that in bits. The software, specifically with the 787, we pulled it apart and put it into two pieces. There's a customer interface bit, which is their optional bits and pieces that they choose, and there's the aircraft simulation. Now, in this, the aircraft simulation bit comes from Boeing. So if they change it, they send us a new bit, and we bolt it in place of the old one. In terms of the time to do it, hour, 2 hours, something like that. As regards recertification, I think it'll be decided between probably Boeing and the FAA. They'll say, this is what we've changed in it. It doesn't materially affect any of these things. So don't need to recertify it till its next regular check or whatever. Or we've made a big change here. We're going to have to recertify it. And then the update on each individual site would be scheduled with the customer for when they could get the approving body to come and recertify it. But the actual physically updating the software is about an hour or two. It's not very long.
As a physical unit, you're taking out one unit.
Well, it runs in that real-time computer that I was talking about. Yeah. And the Boeing part of it, which is quite a lot of megabytes, quite a big piece of software, but it's not that big. And basically, you just replace that element of it, all of the customer focused bits remain the same.
So it is a software.
It's a software package. It's like taking another update to Windows, really. Yeah.
Quick one on that same subject. Are these updates done remotely these days?
Uh,
For instance, would you from Crawley schedule an update to be pushed at a sim in Oz?
We were getting very much that way. Some of the sites we were linked remotely, some of them we weren't. So that was definitely on the up. So I'd imagine probably by now they can do all of those updates remotely. Certain customers didn't want you to be into their system, and certain ones did. Boeing, we could always update the Boeing ones when they released a new piece of software. We could do all of the Boeing training centres remotely, and some of the other ones we could. But I think they were very much moving towards doing that rather than sending someone on a plane with a disk with a bit of software on to spend an hour updating their software.
That's right.
A question about the instrument displays.
Yes?
Presumably today, practically all the instruments are on a flat screen, digital screen. But the compass, they still have a real magnetic compass.
They do, indeed.
at the top.
It's
How do you
always,
simulate that?
that's interesting, that one, because yes, we can't put a real magnetic compass in there. It actually has an electromagnetic thing which we can drive through an analog output to rotate it to the correct position. Yes. Yes.
What about the data model pretty much for simulation? So I imagine when you're developing this, you use like mathematical models of the aircraft for physics and force feedback and things like that. Before the aircraft's built, have you ever had like a situation where the aircraft doesn't feel like the simulator, or is there a place in the development cycle where you have to go back and tweak the models, or does that be certified after that?
I have to say I've not really been involved in that early stage of the development, so I can't really answer that one. I've usually got involved from saying when the thing is almost there. You know, even with the 787, I didn't get onto the 787 program until the first of those simulators was quite well advanced. So the honest answer is I don't really know for that one. Sorry. Yes?
I was just curious about the business case. I don't really have a feel for how much it costs to operate an aircraft to train a pilot. So if you're doing it with a simulator, is it sort of orders of magnitude cheaper?
Well, I don't know the actual list price of a 787 simulator, but I would hazard a guess that it's somewhere between 10 and 15 million, because they're complicated. They've got £1 million worth of parts in them to start with before you even built the thing. You've got all of the development, building and certification in there. But that compares with a real aircraft at, I don't know, 150, 180 million, something like that. It's an order of magnitude difference, at least. So it makes a lot of cost-effective sense to do that.
Do they tend to rent, or would an airliner, commercial airliner company, would they buy their own simulator? Or?
Mixtures. Boeing have got simulator sites and training sites around the world, in America, in Singapore, China, England, of course. Large airlines tend to have their own training centres. So Singapore Airlines, for example, have got their own training centres with a load of trainers. But smaller airlines, like EasyJet, they won't have their own training centres. They will hire time, maybe at Boeing or maybe at the opposition at CAE, and they just hire it by the hour, basically. And they'll book a number of sessions for putting their pilots through, either with their own instructors or they'll hire the instructors as well. Because small airlines, it's too expensive for them to have one and maintain a team of maintainers to look after the simulator, training pilots and so on. Although it's expensive to hire simulator time, it's cost effective for them to do it.
Okay, well, perhaps the last question can be mine.
Yes.
Not a technical one, but what roughly is the timescale for developing a simulator such as the Boeing one you were talking of?
Well, for developing that one from scratch, working with Boeing, it probably took something like 5 to 7 years. It was a long development program of a new aircraft type. If it's a small one, like they were working on the famous 737 MAX, which, of course, Boeing told us was just a 787 with a different engine on it. Obviously, we had all the information about the famous, what do you call it, system? I've forgotten the name of it now.
Stability augmentation.
That's the one. that was coming together quite quickly until they had all of their grounding, and it sort of went on hold for a while they sorted out what they were going to do about it. But because it was, apart from different engines, and obviously where they're fixed, the centre of gravity was different, and that, and the other bits and pieces, most of it was to be fair, a 737, but Boeing really should have told them about that system. I'm just amazed that no one from Boeing actually ended up in jail over it, but I think they jumped ship before it happened.
Okay, it looks as though we're going to have one more question.
Sorry,
Yes.
you mentioned the joint development with Boeing.
Yes.
So Boeing must have given you a lot of their engineers and so on to work with you. Were they doing the same for CAE, for example? I mean, they have to think how much effort they put into developing these things.
I don't think they provided us with engineers to work on it, they provided a lot of engineering information. And I'm sure they must have provided a lot of information to CAE as well, because they had 7-8 simulators on the market more or less the same time. So it's a little after us, but not by years of development. So I think they must have been working with them as well. And if you were Boeing, why wouldn't you? You'd want to keep the two simulator companies viable and providing
Competition.
yeah.
Right. Well, thank you everyone for your attention. Jeremy, we like to give our speakers a couple of little gifts. First, a little certificate, just to prove to your wife that you were actually at a talk, and a little gift. It's actually a power bank, an IET branded power bank. At that.
Oh, well, thank you very much.
Thank you very much. So,
Thank you.
thank you.